And today, like, I'm super glad we have Austin to be talking to us about like GPU CPP. For some context, like this is not the first interesting open source project Austin has worked on. Like I had first heard of Austin from an older project called HaskTorch, which is like basically programming PyTorch in Haskell. And the reason why that blew my mind at the time was because you'd have like these very simple like one line formulas for like gradient descent, and that kind of really blew my mind at the time. And so I'm super glad. And I think since then, like Austin's, continued to do like really cool things. I think at Google, he was working on Gemma CPP, which is also this like very minimal like CPP code base. And I think once he joined Anster, I think he just like went all out and he just like released a GPU CPP. So yeah, really glad to have you here, Austin, and please take it from here.
Yeah, and as a side note, like, kind of part of my initial thinking for this project was when I was doing Gemma CPP, which is like minimal implementation of the Gemma architecture, was I was thinking about, oh, it'd be nice to kind of have some like CPU code. And then when you explore like, okay, well, how can I write CPU code that will just work on people's laptops? It's like all of a sudden things get more complicated than you like. And that was, a little bit of the seed of some of the thinking about this. I'll be talking about this gpu.cpp project, and it's a very small library, and to do this GPU computation in a portable way, and it uses WebGPU. Now, most people here are more familiar with CUDA as a means of accessing the GPU than WebGPU, and that's fine. We'll get more into what WebGPU is and the significance of portability later in the talk. So, yeah, kind of the starting motivation for this project was kind of wanting to carve out space to do both research and development for this kind of local GPU compute. And by local, I mean personal computing devices that we all have, laptops, mobile phones, workstations that are in our house, et cetera, right? So we want to be able to tinker with local GPU compute and to the same level of depth that we think about like innovating large scale training on H100s or optimizations to scale up inference. We want to kind of have that same depth to exploring ideas and projects that run locally, right? Like maybe real-time multimodal models that run locally, or hybrid SIMD with like GPU to share computations, or some sort of hybrid computation between your local machine and servers. And so we wanted to make some space for that, right? And for this audience, this is probably preaching to the choir, but there's a lot of things that are appealing about local GPU that I think are worth exploring in depth, right? And one is to think about scale, right? So usually we think of like MacBook Pro as being very tiny scale compared to the latest cluster that's in big tech. But if you think about it, how many MacBook Pros are sold every year? You have 10 to 30 teraflops of compute for each of those, right? And that's several exaflops of just like M1, M2, M3 MacBook Pros that are out there. Or like another sort of thought experiment, if you think about Pixel 8, Pixel 9 phones that are kind of the first wave of hardware that's sort of influenced by Gen AI applications, right? So like a G3 Tensor Core has about 2.5 teraflops. And if right now those are kind of at the high end of the market, right? But there's 3 billion Android phones out there. In a couple years, high end sort of moves down to sort of consumer side of the market. That's quickly scales to like several zettaflops of compute, right? And we don't usually think of personal compute in this way, in part because it's very inconvenient and very high friction to kind of pull together this compute at the edge. But maybe that's one of the things that's worth exploring. How can you make that more frictionless? Second, I think is everyone here is familiar with local models, and that often is useful to implement against something that's stable that you have fine-grained control over, right? And at that sort of at the individual level, at sort of a society level, we also want to as AI becomes more integrated into important sort of critical systems, we want to make sure failure modes are decorrelated. It's not like, oh, one API endpoint goes offline and suddenly half the robots in the country stop working, right? And along with that, sort of there's classes of use cases that are you want to kind of have a small footprint, right? So things like in medicine, things in law. So it also unlocks certain use cases if you can run things locally, that you might not otherwise not be able to pursue. And finally, like there's kind of new form factors of compute between augmented reality and robotics. And in these form factors, you want low latency. They have high bandwidth video signals, audio signals, and then there's a deeper privacy consideration. So all these are things that speak to, local compute as being not just sort of the realm of hobbyists, but something that we want to study more and more seriously and develop capabilities for, right? So what is it that gets in the way of that? What are some of the things that I ran into when I was kind of thinking about this, um, with like gpu.cpp and other sorts of projects, right? And one issue is that personal devices are very, very heterogeneous, while tooling for GPUs is very vendor specific. So we're used to like vendor specific compilers, vendor specific tool chains. And so you're left with these choices of like, well, I could implement this, but it only works on this one vendor, and then it won't work on most people's laptops. It won't work, it won't transfer over to phones, right? And partly because of this heterogeneity, we've kind of gotten to the state where we're used to accessing the GPU intermediated through some middle layer, right? So something that's usually task specific, right? So in graphics and rendering, a lot of the development happens through the game engines, right? So you use Unity or Unreal engine, and it's the engine that interacts with the GPU directly, right? In our kind of own neighborhood of machine learning, we're used to using machine learning frameworks, and then we're also used to, exporting the model and then putting it into kind of this large runtime framework that handles the direct GPU access for us. And for many use cases, that's sufficient to cover it. But if you want to go outside the beaten path and explore kind of novel algorithms and things, it's not super convenient to then be like, okay, I'm going to operationalize this as a pull request, this giant runtime, a production inference framework or something. So for direct access to the GPU, then there are these GPU APIs. So there's like a Vulkan, that's like a portable GPU API, and WebGPU, I'll say a bit more about that, is another GPU API. But if you use them directly, you immediately find they're very optimized for these kind of large scale sort of middle sort of framework implementations, and they come with like complex builds. So for example, if the ideal is like you want to have, here's my app, I have some C++ code, and I want to just include gpu.h and then start firing off kernels and things. But then the reality is, if I want to launch even the smallest, like TNH, GELU kernel, whatever, in Vulkan, you have 800 lines of code of just like setup. And this is even before you get to any sort of algorithm or anything. And this may seem crazy at first, but it's actually very reasonable. And if you think that the target audience here is for developers of game engines, developers of these like large frameworks and runtimes, right? So part of what I want to do with this project is sort of narrow that gap so that direct access to the GPU is more like sort of just programming. And so that comes with like a few sort of technical goals and how that's implemented. One is sort of avoiding sort of custom tooling, being too custom in that I just want to be able to have a Clang C++ compiler, and that's it. And wanted to think of it as sort of general purpose, right? So we already have these task-specific frameworks. We have plenty of ML frameworks and things. And so to start with, just whatever task, maybe you're working on simulations, maybe we're working on offline rendering, maybe you have a specific, like something like gemma.cpp where you have a specific model implementation. So want it to be general purpose and not sort of another sort of framework. And also want to make sure that we're kind of using something that's sufficiently expressive so that the kinds of optimizations we want to do in CUDA, we can also do them. And have it be portable. So you write your code once and you can move it around between different hardware and easy to embed. And the last piece we were talking about a little bit before we started is like a lot of things are sort of is that one challenge is for something to be widely supported, right? So there are lots of GPU frameworks that are popping up, and GPU APIs that are popping up, but if they don't have like the hardware support, or if they don't have the broad support, it's hard to get traction. So we want to build on something that it seems likely to be widely supported, right? And so that's where we ended up with this implementation, which is this small library. It lets you do general purpose GPU computation, drop it in your code, and we use WebGPU. So I'm going to say, a little bit more about, what is WebGPU, because it is very, very confusing. And the first time you hear it, people hear WebGPU and you think something like WebGL. Like, isn't WebGPU, isn't that like, okay, I have my browser and I use it. Is that what I use to like draw pictures and make little games in the browser? And it can be used for that, but it can also be used for much more than that, right? So the way to think about WebGPU is that it's a spec, it's sort of a generic spec to access the GPU. So to request resources, to allocate buffers, to send compute kernels to the GPU. And so it's this generic specification. The use case they had in mind for that specification initially was to embed it in browsers so that you can have websites that make use of your local GPU compute. So like you go to a website and there's some computation or there's some rendering that's happening that uses your local GPU and gives you access in a controlled, sort of safe and portable way. So it has to be portable in that the browser runs on many different types of hardware, many different vendors, and it has to be sort of generic across vendors. Um, and so that was the motivating use case, was to give GPU access in the browser. But in the process of doing that, they defined the specification, which is adopted across the industry. And then there's also, you have to implement a native implementation, because you have to at least have the implementation that's in the browser. And so when I say native, I mean it runs locally on your machine outside the browser, right? And it turns out that the implementations that were used inside the browser are also, you can use them as implementations that sit outside the browser. So Google's native implementation of the WebGPU specification is called Dawn. It's in C++. And so you can use it as in, if you have a C++ program, you can use Dawn and use the WebGPU API specification to access the GPU, and it'll run across different hardware vendor platforms. There's another implementation in Rust called WGPU. It's also a native implementation. And what's happened is, like in Rust and in some of these other languages, if you ask how do I do GPU programming in Rust, they'll just point you the one of the top choices is just to use WGPU, even if you're not using the browser at all. And then under the hood, what these native implementations are doing is they're translating this API specification into things that are vendor specific. So for Windows, they translate this WebGPU API specification into DirectX, on Apple to Metal, and then on Linux and other platforms to Vulkan. And so it's basically sort of abstracting the vendor specific APIs in terms of this more generic API specification that if you write against this, you can run on all the platforms that support these, right? And then as another option, you can also run it in the browser. But the key point here is it can be used locally outside the browser. So here's a WebGPU, a program, a Hello World, a small program that uses WebGPU that's just running in the terminal. And there's a deeper dive on this called WebGPU is not just about the web. That's worth checking out. And so these are the native implementations. Any questions about that so far?
Yeah, I mean, I will say that's kind of like similar question to when people ask like, is CUDA mode just about CUDA? It's like WebGPU is about just web. But I'm sort of curious to ask here, which is like, does this also work for like server GPUs like with no problem, or does this still require some like web stuff to be like basically
Mm.
some with the Chromium, some parts of Chromium or something need to be installed, or not at
Uh,
all?
no, not at all. So Dawn is basically the implementation of WebGPU inside of Chromium, but it's separated out. So if you have the dependency on Dawn, which is a native implementation, but you don't have a Chromium dependency. Does that make sense?
It does, yeah.
Mhm.
One
Um,
one of the questions that I had initially is basically how like device agnostic can such like a complete cross-platform or cross device thing really be? It's like, is it like the smallest common denominator? How do I
Yeah.
basically query for device capabilities there, and also like
Yes.
how dynamic do I have like
Yeah.
to be?
Yeah. There's definitely a tension there, right? Because as a first order, it's sort of a cut of like the largest common denominator across sort of all the specific GPU APIs, right? But there's always this tension that you want to kind of push further, right? On like, oh, there's this thing that doesn't have 100% support, and then so there's experimental proposals that are always in flux, right? And um, so that's one of the compromises for portability is it will like if the feature is compelling enough, it'll eventually be sort of broadly enough and implemented and incorporated into the standard. But you will lag behind, say, like the cutting edge of what you can do if you commit to one particular vendor platform, right? So that's sort of the trade-off. But it's sort of an ongoing tension that like if something's desirable enough, it sort of works its way into the standard, but with some lag time.
Is
Yeah.
there somewhere a list like which devices are basically supported by this, or for which we is like I guess like AMD and
Mm,
CUDA of course, but
hmm
Intel and others.
Yeah.
So what have you
I
tried out?
yeah, there might be a more official list somewhere. But like maybe like one mental model of it is like if you can run either Vulkan, DirectX, or Metal, then you should be able to run it. Yeah.
Okay, great, great. Yeah, thank you.
Yeah. Um, Right. So kind of next step is like if we use the web GPU API directly, what does that look like, right? And so it looks something like this. So for I have a GELU, activation kernel, which is really tiny implementation, but there's a lot that comes along with it, right? And the web GPU is sort of known as being sort of simpler than Vulkan, so it's about 400 lines of code versus 800 lines of code, but it's still sort of unwieldy enough that there's some cost to just dropping this in a project it tends to be oriented towards people that are developing game engines or inference runtime production runtime or something like that. Um, so uh, uh, so we want to simplify this to make it so that the friction to kind of just dropping in GPU code in a project is a more lighter weight, right? And so if we think about, we really need for if we kind of focus on just the compute workload, so set aside 3D graphics and things like that. So just the compute workloads, there's kind of three main aspects that you have to support in sort of a minimalist library to have to be able to work productively, right? You have to be a way of specifying the GPU, the code that runs on the device, right? So this is kind of the device code in CUDA, and in WebGPU you use this small domain specific language called WebGPU shading language, and then there's also you want to allocate resources ahead of time, right? And this is done as host code in C++, right? And then you have the things you want to do in your hot path, which is you want to kind of minimize any kind of allocation, and then you just want to do asynchronous kernel dispatches as fast as possible, um, with sort of minimal data movement and minimal sort of resource allocation, right? So if we can kind of come up with a sort of a minimal set of types and functions that do this, we can then simplify this into something this small, which is should be probably a little bit more familiar that if you're familiar with CUDA, you can probably squint at this and kind of figure out what's going on. So you have your device code that's written in this domain specific language. If you want, you can embed that in your C++ code as sort of like a quoted string, or you can kind of have it in a separate file if that's what you prefer. And then you have the host code to set up resources and then do this asynchronous dispatch. And we'll do a closer look at this in a bit after looking at a couple of these like types and functions that are part of the library. So to use a library, you just include this gpu.h, and this core implementation is only about 1,000 lines of code. So that means, when you're compiling, this is pretty much close to instantaneous and very little sort of overhead in terms of your compile time iterations. On the device code, it looks like this. It sort of looks C-like language, right? But focus on sort of computations that you can carry out on device, plus some metadata on sort of the bindings of that you share between the host code and the device code. This work group size is sort of the WebGPU equivalent of blocks. So you can think of it that way. And like CUDA code, you have this kind of identifier for which thread ID it is, and then you write your kind of your computation in terms of this like thread ID identifier combined with some of the block size information and things like that. On the host side, we have a couple like supporting types and functions to kind of do the things you want to do with allocating resources and dispatching kernels. So we have this context type, which is sort of like a simplified way of interacting with the GPU. So if you look at the raw WebGPU API, there's a whole bunch of other things that are happening under the hood here. But here, if you basically it's a simplified. If you want to talk to the GPU, you use this context handle. We have this kind of tensor, which is just a wrapper around allocations of GPU memory. So it's kind of these like flat linear buffers. And then the representation of the computation to run on the GPU is this kernel type, which sort of wraps this WGSL program and also ties that to buffers, GPU buffers that it had that computation has access to. So it's kind of connecting the WGSL code with these whatever allocations you want to provide for it. And so you request these resources through these factory functions to create the context tensor and the kernel. And then when you have those resources prepared, then you can asynchronously dispatch and block on the dispatch if you want to block. And then you have some helper functions to move data back and forth between the GPU and CPU, right? And there's a few other supporting types just to configure some of these types. And specifying the dimensions of the tensor. You have kind of wrap around the code for the kernel, the bindings between the kernel and the GPU buffers, and some internal things here. So coming back to this hello world implementation on the host, we saw the WGSL on the device side. On the host side, we can take a closer look here. So the things that are in this gpu.h are inside this GPU namespace. And here we request the context. So that gets us handle to the GPU device. We just create some dummy data, just regular C++ code there, right? Oops. And then we allocate GPU buffers and we create the kernel binding the GPU buffers here. And then we specify the number of work groups, just like we specify the number of blocks. And then here we launch an asynchronous dispatch. We wait on the dispatch to finish, and we copy the data back and we print it to the screen. So, so not that much different from kind of what if you were to kind of do the equivalent functionality in CUDA, right? And maybe one last sort of quality of life thing to mention here is that normally if you kind of incorporate this native WebGPU Dawn implementation, it is a pretty big implementation, right? Because it's like got to implement all the backends to the different vendor specific APIs. And it can be kind of a bit of a pain point to wait for the build to finish in 5 to 10 minutes. So, as like, I want this to be more like PyTorch kind of thing, where it's like, I don't wait for libtorch to compile every time I'm kind of like writing code. So we provide some shared libraries, and that makes this compile cycle instantaneous, right? So instead of waiting for 5-10 minutes for kind of the Dawn dependency to build, you just link the shared library for Dawn, and then the only thing you're compiling is whatever snippet your code is, like that for the defining the GPU computation and that gpu.h, which is only 1,000 lines of code. And then so you basically build instantaneously to the point where it's interactive. You can just leave it running and keep building as you're editing code.
So there's a
Yes.
question from Vikram. How do you do
Mhm.
asynchronous dispatch? Is this with coroutine or have you used the Vulkan approach?
This is so this is just so it's the calling into the dispatch of WebGPU is asynchronous by default, and then we're using just promises that are built into C++ for now. There is I I think it's coming soon. Like a WebGPU will have its own kind of promises and futures. But does that answer your question?
Um,
So yeah.
yes, yes,
Yeah.
it does.
Um, okay. So right. So just to have another example that's not everything is AI oriented. If we want a little physics simulation of double pendulums, and you can start with thousands, you can ramp it up to millions. And what this is showing here is just kind of the joints of the double pendulum of sort of an ensemble of double pendulums with kind of different initial conditions. You can kind of see how this same pattern plays out. I have my simulation code, which is sort of like the physics, sort of writing sort of the state transition function of the physics for one step of the simulation for one particular simulation. And then on the host side, we allocate some GPU buffers, set up the kernel, and then I have a hot path where I'm basically iterating over the simulation. And each time for however number of simulations I have, I dispatch the kernel, and then I print out the picture and come back. Right. One thing that we get for free is that because the GPU compute kernel code is um, is in this WGSL, it's in its own little language, which is you can have inside your program as a string. We can hot load the GPU code um, without doing any sort of recompilation. So at runtime, you can swap in different GPU kernels and just keep the execution running. So what this is showing here is a clone. If you're familiar with ShaderToy, you can think of it as a compute kernel that's a function of three inputs. One is the X and Y coordinate here of this like ASCII kind of grid, and then also time. And so all of these animations are functions of sort of X, Y, and time, and you can make all kinds of pictures just with by returning a intensity value for each of those for that function. And so your compute kernel is implementing that XY time function. And what you're seeing here is I'm basically copying in different code into that kernel as this program's running and swapping in a different compute kernel, and it just keeps running. One kind of like emergent thing that comes out of this is that um, I'm just checking to see if the code changes and reload it, but I don't clear the GPU buffers. And so you get these like transitions from one animation to the next just by virtue of the GPU buffer state just being the same between swapping out the compute kernel that's underlying it. So this is really kind of to demonstrate this kind of like ability to sort of runtime swap in different GPU kernels in your application. Another kind of example is that we were playing around with matrix multiplication implementation on my little M1 laptop. And the goal here isn't necessarily to create like a production matrix multiplication, but to go through this exercise of Simon Boehm has this now famous sort of blog post of CUDA matmul kernel work log, and it and throughout it starts from this kind of naive kernel and step by step add sort of more and more optimizations, right? So what we want to kind of make sure is that like we can take these kind of optimizations step by step in the CUDA world and try them out in this WGSL implementation in gpu.cpp and WebGPU, and just check that we can do that, right? So we start out with this naive implementation that just does sort of the dot product per thread, and that starts us off at sort of 284 gigaflops here. And for those of you that remember the first GPU CUDA mode talks from Jeremy's talk was like, well, you want to go from that to this shared memory tiling um, procedure. And with shared memory tiling, you go basically get 3x improvement to about 629 gigaflops. And then, so Simon's post goes beyond that of you want sort of to do more computation per thread. So you do this block tiling where you kind of do this kind of multiple sort of blocks per thread, and iterate over the matrix that way, and that takes you to 1.2 teraflops. And then you take that one step further to get even sort of more compute per thread of this 2D block tiling that takes you to 2.4 teraflops. And then you can keep going from there. You can swap in float 16. You can unroll your loops, and takes you to 4.9 teraflops on M1 laptop. And you can keep going with this, but this is kind of where we are for now. And of just so the idea here was basically to try this kind of sequence of optimizations and see how it feel to try this out in this WebGPU context. And it's not that different, right? So a lot of the same things you can express in CUDA, you can express at least for that blog post, you can kind of you can do in this way as well.
Austin, I have a question. So like just
Sure.
the previous slide.
Yeah. Yeah.
Yeah. Like the syntax sort of looks similar to CUDA, but not like quite. So I was wondering if you could like talk more about like your taste here and like
Yeah.
why you decided to deviate in some ways.
Right. Um, so the syntax, so to be clear, we don't define the syntax for WGSL. So WebGPU shading language is part of the WebGPU standard. So we are piggybacking on the this definition of how you express a compute kernel in WGSL. There's a few conveniences we have to embed some substitutions, right? So here you can see kind of this tile size is like a parameter that I swap in. But for the most part, the syntax here is whatever the WGSL syntax is. We could have implemented something that's like maybe like one layer above that sort of compiles down to this. But for now, it made more sense since the whole point of this is sort of direct access to GPU. We sort of just make use of this open standard, right? Because there's a lot of mature options for compiling down to low level kernel code, and the point of this project wasn't to add sort of one more way of compiling down to kernel code. It's just you can write kernel code. WebGPU has this sort of kernel code language in the form of this the WebGPU shader language, and so we make use of that. Does that answer your question, or were you asking something else?
Like parts of it. Like I think let me see how to re-ask this. So it seems to me like I mean like let's say when you mentioned the tile size stuff like that sounds like
Hmm.
like someone is like looking at like WGSL and is thinking like what would be like nice functionality from like CUDA or things that people would want to express like when writing CUDA programs and how do we
Hmm.
make those like really built in into the language and sort of really convenient to use? Is that like an accurate way of describing GPU.cpp?
I would say that like it's less us making an intentional choice to especially on the device code side, less us making an intentional choice and more just that the basic things that WGSL can express have overlap with sort of the basic things that CUDA expresses, right? So the aspect that we have that is sort of more of our specific taste is more on like the host side code where we are kind of wrapping the more verbose low-level web GPU. On the device code side, we're mostly kind of following whatever the lead of the web GPU standard and maybe adding a few things to like splice in some templating thing in the code, but not trying to like make our own, not trying to have too much of a layer on top of just writing the raw web GPU shading language code.
Okay, yeah, that makes
Yeah.
more sense.
So,
And
so a
maybe
quick
Yep.
question, like directly to the code that we see here on the slide. So this in double braces things like which look like template variables. So this is basically like constants, or what? How it is?
Yeah. Those are things that get substituted in. You can not do so. So this basically there's a pass where it sort of substitutes for some of these variables. You can not have that. You can also, as an option, you can pass in variables into the WGSL code and then just treat it as like a regular variable. Nice thing about this is just like there's no overhead. So there's a it basically replaces these with some constants before it even passes that to WGSL. So what actually here in this version here, This is actually the code that gets passed in, so it would just be like regular code. So those substitutions get spliced in, and then it gets sent to the Dawn implementation to kind of read it in as WGSL code.
Super nice.
Does that
And
make sense?
how long does the like compilation of such a kernel take? So
Mm.
it's always like in a string, basically. So it's no add of time compiling, as I understand. So and it's then at some
Uh,
point it needs to be like before you like launch the kernel, it needs to be compiled somehow, right?
yeah. That's a good point, right? So for our standpoint, we're not implementing a compiler at all, right? So we have like some substitutions, and that's it. On the WebGPU implementation side, it takes it in as a string as well. Now, so the important thing is you want to keep that loading of that code outside of your hot path. So you do it on program initialization or something like that. Um, and so so you wouldn't like pass this in kind of the hot and sort of the hot path of your code. This is kind of the design of WebGPU is that they don't do like any heavy compilation. So it's almost more of like a one-to-one transpilation. So let's say if you have the Vulkan backend, it's almost like transpiling this to Vulkan and SPIRV, and then does its thing there. So even the dominant implementation isn't doing like for the most part doing like optimization passes or things like that. So the idea is WGSL is sort of like this shallow transpilation to the kind of the backends. But this is kind of one design thing that's been debated in WebGPU is like, would it be better to have some like SPIRV IR, or would it have been better if like SPIRV was like part of the WebGPU specification? Um, but for our purposes, we're working with kind of this is the WebGPU spec as is, and there's probably debates to be had on, do you want to should you have some IR or something like that's kind of more part of the spec. But for now, it's like you have this code, it has a shallow transpilation to kind of the like DirectX specific or metal specific shaders, and and mostly you want to take care of. That's why you do the create kernel outside of the hot path of your code, so that you're not doing that in some of the low level loop. Um, does that answer your question?
Yeah, thank you very much for the
Yeah.
clarification.
Yeah. But this is very hotly debated if you look around the web GPU discussions. This is actually one of the most hotly debated things. Um, so it's definitely good question to be asking. Um, okay, so for a far more kind of introductory level um, thing. So there's a set of great sort of tutorials by Sasha Rush called GPU puzzles. And this is basically like a tutorial on GPU programming. You can implement them in Numba, and normally you do them in a notebook on some machine that has like an NVIDIA GPU or something like that. And we thought it would be really nice to kind of have something like this as a tutorial to using WebGPU and gpu.cpp as well. Um, because a lot of all the same concepts sort of transfer over. So Sarah Pan, who's a student researcher and MIT student at Answer AI, went through the GPU puzzles and implemented a version that's implemented with gpu.cpp and WGSL code one by one from the beginning to end. From kind of, and this sort of starts with like these very simple operations, like a map operation that's spread across GPU threads to zip operations, working up to dot product and a matrix multiplication. Shared memory is kind of the last puzzle here. And so you can run these, you can try these yourself in the examples directory, and you can run it locally and use it as kind of a tutorial in that sense. But one of the things we thought that would be nice is, well, it'd be nice to have like a little tutorial app to make this more interactive. And so that brings me back to kind of this point that I've been saying kind of for the whole talk is that like, WebGPU, we can use it as this native GPU API. It's not just for browsers, but then one nice thing about it is that we have this option to also target the browser if we want to, if we want to, right? And so we can do that by taking advantage of compiling our C++ code to WebAssembly with mscriptum, and then the browser has its own GPU implementation. So you can think of it as like, yeah, that same sort of API shim. Instead of going to our local Dawn implementation, it goes to your Chrome browser's implementation of the WGPU WebGPU spec. And so we can take advantage of that. And we used, if you've been following other Answer AI projects and things that Jeremy's been doing, there's this fast HTML framework. So we can create a little web app in fast HTML and stick this client side GPU compute there and make a little app out of that. And so here I have a web app, but instead of the GPU running on a server with an NVIDIA GPU on it, it can use whatever GPU I have. So if all you have on your machine is like a wimpy little like integrated GPU, it can make use of that. If you have a local NVIDIA device GPU, it can make use of that as well. And so I can play with this here, right? And each time I make an edit, it's running the computation and checking the correctness, and it's running that on my local GPU. And so, oops, here we go. Okay. And so it's every time I type, it's sort of writing this compute kernel. So it's basically taking the compute kernel that I'm editing here and continue every time I type a letter, it executes that compute kernel until you get the correct answer, and you can look at the solution. And so yeah, I've embedded this this local compute into this web application. And so this is kind of
And you've
a
embedded the
modest.
web application into the slides, which is kind of mind-blowing.
Yes, yeah. So this is a browser-based slide. So yeah. It's in the presentation,
So,
and
so, so
yes,
very
sure.
curious here. Like, I mean, because like this all doesn't seem like a coincidence. Like both you and Jeremy being so interested in like web development, and so I'm curious, like how you're what you're thinking. Like, I mean, there's sort of like the obvious benefit from a teaching perspective, where a lot of
Hmm.
people in Kudamoto are like, well, how do I get started? Like, I don't have a GPU, like, and then we tell them collab or whatever. But this seems like a much more reasonable first step because it just comes to it's just your laptop, right? So I'm
Hmm.
sort of curious, like, whether are you primarily thinking about teaching, or is there something else that like you've been curious about longer term?
um I'd say like longer term, um in some sense it gets back to some of the motivations I mentioned in kind of the initial slide, right? That like um we have, if you think about sort of the world's worth of local compute, it's quite a lot of compute, right? But it's mostly challenging to activate, right? And so if you have the option of like, oh, I can kind of bring any amount of GPU, local GPUs online just by someone opening a tab, then there's a whole bunch of use cases and ways of using the GPU that are otherwise might not be available, right? And uh, so yeah, without getting kind of too long term, that's I think that's a very pretty, like, this is a kind of a small, more pedagogically oriented test case of that. But I think there's something very compelling about that, of having GPU available um, uh, just by opening a tab.
So will you
Like,
have like an LLM implementation also?
A what implementation?
Yeah, like of a large language model to run it in the browser.
There, I
I
mean,
mean, there
so
are
there
already.
are, yes, there are like kind of proof of concepts around that. So like the TVM team and LLM MLC, I think is the name of the project. So this is already very possible. It's still, I would say, early days, because it wasn't until last year that the Chrome flipped the flag from like, this is a kind of alpha. It's still kind of early testing, but now they've kind of made it so that it is enabled in Chrome. So it's still pretty early days for like what is a space of use cases that this unlocks. Um, but yeah, I think it is feasible to run LLMs and things just by opening a browser, and it will run locally. Other questions? All right. So yeah, so with that, I'll wrap up. Wanted to thank, everyone, Answer AI, who's kind of been helping feedback on the project and trying things out, as well as friends on the Discord channel. You can find out more at gpu.cpp.answerAI and check out our GitHub here. And with that, maybe I'll pause, take any additional questions, comments. All right, thanks everyone.
Yeah,
This
thank
was
you,
pretty
Austin.
sick, Austin. Thank you. Yeah, like,
Awesome
you have
talk.
an infectious energy. Thank you. This was great. Um, so like folks, if folks have any questions to Austin, uh, please let us know. Like I have one, and I'm gonna read some from chat already. So Vikram is asking, does WebGPU support tensor cores?
Yes, not yet, but it's something that's in discussion, right? This is one of those things in terms of the lifetime of like portability. But I can point you to a couple issues to track if you're interested in that.
Stefan is asking, is there support for using multiple GPUs at once for
Yes.
collectives?
Yeah. So with the native implementations, there's a way to do this. For the web implementation, not yet.
Okay, so Feynman has a question. I'm gonna sort of paraphrase it a bit.
Sure.
Have you considered building a higher level ML framework on top of WebGPU?
Um, for now, how would I say? I think for now, like if you want to do like a full ML framework, the shorter path is probably I suspect there'll be ways of compiling like Jackson PyTorch code to WebGPU. So I think those there if you string together sort of the right compiler change, I think that there's ways to do that. We will explore kind of maybe instead of going from this kind of top down, going from the bottom up and implementing like LLM.C kernels, like porting those over. So and it's more kind of from the perspective of like if you want to do some sort of bespoke implementation, or you want to implement something where you have like fine-grained control that would be difficult to do going through like compilers and IRs. Then you have here's kind of a small library of like kernels you can kind of tie together into kind of what you want to implement. So coming from that kind of bottom up direction more than trying to create like another ML framework.
I had a question. So like,
Sure.
one thing I noticed is that a lot of your contributors did like a really nice job of taking very popular tutorials and like basically revamping them in a way so like they're more accessible. So I think you
Mm,
mentioned Sarah Pan's work. So I'm sort of
mm.
curious if there's any more such projects that you think would be a good fit for people that are getting started in systems
Uh,
programming.
yeah, actually, probably like a wish list of like pedagogical things that would be cool. One thing that would be I was thinking about is like some sort of like auto diff would be really cool, right? Because I feel like that would also lend itself to something to see auto diff like interactively in the web would be I feel like that would be pretty neat. Um, I don't I probably may have to think of offline, but if you're interested, yeah, I feel like there's like a lot of things that would be pretty interesting to implement like pedagogically, and then like yeah, this sort of like web application way of presenting it, that like opens up a new ways of like to sort of like sharing that pedagogy.
Big
You
shout out
seem
to
to,
Sarah, by the way. I just wanted to mention Sarah joined us when she was still at high school, and
wow.
this is the first project that she's worked on. So it's fantastic to see from her.
Yeah, here's
Nice.
awesome.
Austin, how do you normally do the like, debugging in this like web GPU cases? Is it that because I guess like the C code is like you can just use a normal debugger for it, but
Uh-huh.
then as soon as you have like kernels, probably you'll have some strategy to um
Uh,
yeah.
yeah, yeah. I mean, kernels. It's always yes. Uh, Yeah, I mean, I have my own maybe kind of tricks and hacks and things, but like one thing is like I will use kind of the output, right, of the kernel in various ways to like check the state of things, right? So for actually, I can show you this here, right? So like let's say I'm kind of confused about like my thread ID or something, I can like do something like this, right? And I can see, oh, what LID X am I going to see? And I can see that here, right? So we can kind of, and this is one reason why I also like the sort of the fast sort of compilation cycle, or even sort of hot reloading is so valuable. Is like, yeah, you can like drop in kind of things to try and kind of instantly see that feedback without waiting like 40 seconds or a minute for like everything to compile back on again, right? So it's like here I can kind of play with this in real time. And for some of the trickier puzzles, that becomes like pretty useful once you get to, doing this sort of thing where it's like, yeah, I won't live. Maybe we can have a streaming session or something later if people want to see me try to
Regarding this,
do
what we see here, the GPU puzzles, are they like the UI? Is it like written in JavaScript, or is it like in how is it like
so
interface facing basically now with the WebAssembly stuff?
yeah. So the layout is all like fast HTML.
Mhm.
And then some of the
Right.
client side logic is mostly WebAssembly and then a little bit of JavaScript for some of the state handling. I think like in the back of my mind, there's probably ways you can wrap this so that it's all like fast HTML, component wrappers, and then you can do it all in fast HTML. But like as sort of the being the guinea pig of trying this out, there's some sort of JavaScript that's sort of implementing some of the state logic here. But
So
all
just for
like the
people
visual
who aren't
representation is
familiar, Fast HTML is a Python server which largely serves HTMX, HTML partials. So it's kind of a bit of a mishmash between client and server.
Mhm. Yeah.
I see this like Jeremy wakes up and then feels like there's something missing and we need to build it. It's like for fast HTML. Yeah. Very nice.
Uh, Austin, one thing I wanted to ask you is like you briefly mentioned visualizing autodiff. So I have a more general question here. Have you found it useful to visualize machine learning kernels visually? And if so, like, do you have any example that was notable?
Uh, I would love to see more of that. Yeah, I'm sure and I've seen like some like YouTube tutorials where it's very uh but I think it's like very to visualize sort of like compute kernels is like very uh someone does some painstaking I don't know D3JS or OpenGL thing. Um I yeah, so we haven't I think like maybe one if that happens like that there's a cool side effect that like you can implement compute kernels and then you can drop it in them into some visualization. That would be awesome, right? But it's still early days, right? So I would love to see more compute kernel visualizations, right? Like we need more visualizations of like flash attention or something, right? So yeah, I'd love to see more of that. Um
Uh, Polyonics is asking, are you guys aware of Godbolt and the compiler explorer having real-time CUDA execution?
I'm more of a Godbolt, and I've seen the CUDA execution in that. Um, yeah. I excuse me. I assume it's using something with WebAssembly under the hood, but I don't know how it's doing the CUDA stuff. Um, yeah, yeah. Actually, a good example of Godbolt is in this Simon Boehm's blog post where each of the implementations has its own link to a Godbolt implementation here. Um,
Yeah, so Polyonics is saying like in Godbolt it's not local.
oh,
It's
I see, I
like
see.
yeah. I think they just have like GPUs in the back end, like and um
I see.
so so Gaurav is asking like about like what are the requirements and limitations to embed web GPU applications across the web, like anything that works and what does like what works and what doesn't.
Yeah, yeah. What's nice is that so coming back to this picture, right? So most platforms that are able to do Vulkan, DirectX, and Metal, you should be able to target it. And so that's quite a lot of surface area between those three. I'm sure when you get into the nitty-gritty, like if you have sort of more and more complex applications, you might run into things where it's like, oh, I need this particular capability, and like, float 16 or whatever, and maybe you have to deal with some of that those compatibility issues. But to a first approximation, you can look at sort of what things can you target with these three backends, and then it should at least be feasible.
So if you can maybe like wrap it a little bit up and summarize what is like the primary use cases for WebGPU and GPU-CPP.
Yeah.
So I already say, so the education is of course like one of the and like trying out things, and also like covering like this like broad range of different devices.
Yeah. So kind of going back to the point at the beginning of this, like the space of like local compute, right? To be able to experiment with the same degree of depth that we think about, writing CUDA code, to think about, what are some things, what are some new directions we can take when the compute is local, um, and yeah, and having the option to sort of target the browser and take advantage of local compute on the browser is an opens up an additional set of use cases.
Just thinking about like crazy things that could be like you just load a web page and then like you run, you're part of a distributed trading run or something like that. I don't know.
Yes.
Maybe we'll see in the future.
Yeah, there's a part of me, I don't know if people ever saw the TensorFlow playground. I feel like there's something to that kind of got left behind, that never got fully explored.
Yeah, it's like doing this for like really larger like networks and so on, which will require a little bit more than just like JavaScript, and
yeah, and I think there's a whole space of like, if you start co-designing for that, right? So you think about like, oh, maybe I have a huge amount of parallel compute for everyone that's like opening the browser at this place, but sort of the communication between them is limited. Maybe that leads to different directions in terms of how you think about model architecture, algorithms, and things like that. That would be super interesting to explore.
Yeah, super great. Thank you very much, Austin, for this awesome talk and the presentation of GPU-CPP.
All right, thanks so much, everybody.
All right, thanks everyone. But please make sure to shower like Austin with emojis, and he'll be in CUDA mode if you have any more questions about like about WebGPU and GPU-CPP. Thank you, Austin. Honestly, this was great.
All right, take care, everyone.